Welcome to Lesson 5 of Inventive Problem Solving. Today we're going to look at additional tools for resolving contradictions. And in particular, we're going to look at separation principles, which are designed to tackle physical contradictions, as contrasted with the innovative operators or inventive principles that we learned in the previous lesson, which were targeted primarily to technical contradictions. Allow me to remind you once again that inventive solutions to problems involve resolution of contradictions. And recall that there were two types of contradictions, the technical contradictions and the physical contradictions. The latter being a situation in which a characteristic of a system must exist in two states or something must be both absent and present. This is where the principle of separation comes to the rescue. So let's say we have a thing or a function that produces a good thing, but also produces a bad thing. So therein lies the contradiction. What separation says is that we take that thing or function and break it into two sub-functions or two states of that function, wherein one function produces the useful effect and the other function counteracts the harmful effect. There are actually four separation principles. Here they are: separation in space, separation in time, separation between the parts and the whole, and separation upon conditions. Let's look first at separation in space. If a system is required to perform contradictory functions or operate under contradictory conditions, we try to partition the system by assigning each contradictory function or condition to a different physical spatial location. For example, a situation in which a characteristic is large in one place and small in another, or where a characteristic is present in one place and then absent in another. Here's my classic example, the problem of a bandage. It needs to be adhesive to remain attached to the wound, but it needs to be non-adhesive to avoid trauma to the wound. So therein is a physical contradiction. So the solution, as we all know, is the Band-Aid. And you see how there's a separation in space, that a portion of the Band-Aid has the sticky stuff on it to hold it in place, but the portion that is directly on top of the wound is non-adhesive. And as a matter of fact, the different layers of that central section are also separated. You might remember that there's a thin plastic film that separates the wound from the absorbent white part of the Band-Aid. So this seems relatively obvious and straightforward, but at one point in time, let's say 1957, there was no such thing as a Band-Aid. Wounds were wrapped pretty much the way you see them in the upper image, the way they were wrapped during the Civil War and probably long before. So if they had given some thought to the separation in space principle, they may have actually invented the Band-Aid much earlier. I'll also just qualify that, of course, there is a enabling technology that needed to be invented, plastic perhaps being one of them, but adhesive, and that is really one of the breakthroughs of Johnson & Johnson. So now applying that same logic, now we have a Band-Aid. It's persisted for a long time. They look pretty much the same. Doesn't that imply to you that there's an opportunity for innovation? And does it ever make you wonder what could possibly be beyond the Band-Aid? We can always consider ideality when we ask ourselves this question. Is there any of the useful functions of the Band-Aid that could be made more useful or improved? Or are there any harmful functions associated with the Band-Aid? And these are relatively obvious, so I don't need to point them out to you. But one technology that's catching on, it's actually been around for a while, but it's getting some traction, and I see it appearing in the drugstores, is this gelatinous, hydrophilic, um, artificial skin-like material. Duoderm is one such brand of this material. And this could potentially be the next generation of what we consider to be a Band-Aid, or maybe not. Here's just one other example that I stumbled across while preparing for this lecture. It was found on a website known as gearports.com newsletter. And it shows something of a smart Band-Aid, incorporating sensors into the Band-Aid for any number of reasons. I want to just point out a portion of the statement that accompanies the image. They state that sweat carries a trove of valuable information. If we're thinking in terms of TRIZ, we should see a statement like that as pointing to the existence of resources. Secondly, we'll notice that one of the enabling technologies is the nanotechnology that allows us to even contemplate such a small, flexible type of sensor that could be incorporated into something like a Band-Aid and also be cost effective. Here's another basic illustration of separation in space. Let's take this example of a simple beam that's supporting a lot of weight. The contradiction is that the beam needs to be strong and stiff so as to minimize flexure and to not break, but stiffness requires the beam to be thicker, and that's going to add weight. And weight is both costly and it adds to the original problem of flexion, so it actually decreases the amount of capacity. So the brute force solution is simply use a thicker beam. But here's the contradiction. The larger the beam, okay, we get more strength, but now we use more material, it creates more weight, and because it's heavier, now there's less carrying capacity. So there's an obvious physical contradiction. We saw this before when we talked about the difference between trade-offs and inventions. So making it bigger is an example of a trade-off, and altering the topology is an example of something inventive. And that alteration or that invention is an illustration of a separation principle. So let's analyze this problem in a little bit more detail and conduct a cursory exercise of identifying resources. So there is always gravity. There's obviously mass of the beam, mass of the load, and any number of other resources like air and water and surface area, etc. But I'd like to point out in analyzing the resources, we have two-dimensional resources. There's the length of the beam and the cross-section. And that implies that there's two opportunities for applying separation in space. So if we apply separation along the span of the beam, we can consider putting thickness where the bending moment is the greatest, near the supports, and making it thinner where the bending moment is the least, in the middle of the span, which is a very common construct that I'm sure you've seen. Okay, another application of separation in space is in the opposite or perpendicular direction. We realize that at the center of the beam, at what we call the neutral axis, the material really isn't doing very much. Where it's really needed is above and below the neutral axis. So if we move the material in this fashion, forming an eye, we now have made much better use of the material and highly increased the stiffness with less weight. And this again is a very common construct that was invented at some point in time, who knows when, but it basically followed the same logic, the same principle, which at the time they may or may not have known is separation in space. But now that we have this example, we can apply this in other problems that are similar. Okay, here's an example of separation in time. Looking at an airplane wing. Okay, you may remember that a wing is shaped in a certain way so as to create a low pressure area and a high pressure area. And that creates lift, which is a good thing. But it also creates drag, which is a bad thing. Well, depending on the shape of what's called the camber line, the shape of the airfoil, and the angle of attack, you can alter the amount of lift and drag. So you see in this central image, the steeper the angle of attack, the more lift, but also the more drag. During takeoff, we need a lot of lift, so we want to incline the wing or the airfoil steeply. But that's going to cause a tremendous amount of wasted energy and hence fuel when cruising. So that's when you want the wing to be basically straight or minimize the drag. So how do we address this contradiction? On the one hand, we want to increase the camber to produce more lift, but in doing so, we've created more drag. So applying separation in time results in an inventive solution that I'm sure you've seen before. Separation in time says to schedule a process so that conflicting requirements, functions, or operations take place at different times. In other words, a characteristic is made large at one time and small at another, or a characteristic is present at one time and absent at another. So when we're taking off, we want there to be a large angle of attack. We want there to be a great deal of lift, and we're willing to pay the price of additional drag. And this is where this sectioned airfoil comes into play, or the addition of flaps to an airplane wing. When cruising, we lift the flaps, we change the shape of the airfoil, and thereby achieve the optimal shape for that particular time during cruising. Here's another simple example of the booster rocket. It's necessary and present at takeoff in order to provide the required enormous amount of fuel and thrust to escape the Earth's gravitational pull. But once the fuel is consumed, now it represents an unnecessary amount of bulk and weight. So it's made sectional so that the shuttle can be separated from the booster and it can be discarded for cruise. Moving on now to a medical example, that of a vascular catheter. If you've ever had one of these inserted or seen one inserted, you understand this is a tube that needs to somehow get plugged into your vein. And to do so, it obviously needs to be stiff in order to penetrate the skin and get into the vessel. On the other hand, once it's in place, you don't want it to remain stiff because it can cause trauma and pain. So the contradiction is the stiffness of this device is necessary to be effective for its initial function of venipuncture, but once in place, it produces pain and trauma. And the fact that we can recognize that these contradictory requirements occur at different points in time tells us that we can use separation in time. So the solution is to insert a rigid needle inside of a flexible catheter. Then out of the end of that catheter is the sharp end of the needle. It penetrates into the vein, and once everything is in place, the needle is removed and the connection is made. This is an example of a very simple looking invention device that makes an enormous amount of money for companies like Becton Dickinson. And every little tweak and improvement that you can make on this can steal market share away from this monolithic company. Just for good measure, although we haven't gotten into it, it's also an example of separation between parts and whole. And if you were noticing, we may have spoken about this in an earlier class, this is an obvious example of nesting. Here's another quick medical example, something known as a thermoplastic splint, or sometimes used as a cast. It's a sheet of material that you can heat with a blow dryer or in an oven, or sometimes in hot water, to make it malleable. And now you can shape it around your wrist or your ankle or your knee and conformal to your anatomy. Then once it cools to room temperature, it becomes rigid. So it's obviously a very clever invention that very rapidly allows you to apply and immediately use this cast. Unlike a plaster cast, which is first of all messy, and second of all takes a bit of time in order to harden. The contradiction here that it solves is the fact that you want stiffness in order to produce splinting, but that stiffness makes it difficult to form, so you need it to be soft at a different point in time, and hence the need for separation in time. You may also notice the inventive operator, inventive principle 36, phase transition. The air cast is another example that we saw earlier, which is another illustration of separation in time. And here you may recognize inventive principle 29, pneumatics. And just again, for good measure, this is also a case of separation under conditions, because under one condition where air is not present or there is no pressure in the cast, it's flexible. And then later, when pressure or air is applied, it becomes rigid. The next separation principle is known as separation between the parts and the whole, or sometimes separation of structure. It's based on the premise that every system, almost everything, can be broken down into smaller and smaller parts. And once you recognize that, you can recognize that parts can be added or subtracted or altered in some way, so that the whole is greater than sum of the parts or behaves differently than the sum of the parts. Here comes an illustration. Here's a classic illustration of separation between parts and the whole. A bicycle chain. If you think about it, it needs to be stiff in the longitudinal direction so as to convey tension and hence torque, but on the other hand, it needs to be flexible in the perpendicular direction so that it can go around the various sprockets. This is a subtype of separation principle 3, wherein a characteristic has one value at the system level and an opposite value at the component level. You may also recognize inventive principle number 1, segmentation, which we saw earlier. The other subtype of separation between parts and the whole is a characteristic exists at a system level and does not exist at the component level, or vice versa. So a classic example is two-part epoxy. When they are separate, they're liquids, and they can be formed and injected into crevices and between parts that need to be bonded together. But then once mixed, with the passing of time, they become solid. Separation between parts and the whole. Having now seen the bicycle chain example, you'll recognize this as another illustration of separation of parts and the whole. This is a carpenter's ruler that carpenters love because it's stiff on the one hand and yet flexible so as to easily fit in the pocket or fit into a toolbox. Another similar kind of product I saw in a catalog once, and I made a note of it, is this clever looking ruler that folds up into a little cube that you could put in your briefcase or in your pocket. So on the one hand, it's flexible, it's limp in one dimension, but if you rotate it 90 degrees, now it becomes stiff. Or if you put it on a table, it's stiff and straight and allows you to measure, but once you pick it up, it becomes foldable. So this is also arguably separation under conditions.
Speaking of which, separation under conditions is defined as a characteristic is, let's say, high under one condition, low under another condition, large under one condition, small under another condition, heavy, light, present, absent. So here's a nice little example. Portable exercise barbells. For those of you that like to use free weights and do a lot of traveling, here's a very lightweight barbell that uses water as the source of weight. So the contradiction can be described. You want it to be heavy so that you can actually get some exercise. But on the other hand, you want it to be light, and you also want it to be small. So using resources, which is the water that's in your hotel room, you can create these weights and solve that kind.
This is another subtype of separation upon conditions. This is when a characteristic is present under one condition and absent under another condition. And the illustration is these graphics that you see on buses and other vehicles. Have you ever wondered how it's possible to not be able to see into the bus, but yet when you're on the inside, you can actually see out through this artwork? This is how it works, in case you didn't know. That artwork, at least where the windows are located, is porous. So when you're inside the bus, looking out, you can see through these little holes because it's dark in the bus and it's bright outside, and therefore the brightness overpowers the darkness. When you're outside, the sun reflects off of the graphic part of that porous media, and it overpowers the darkness of what's inside the bus. You may also recognize the use of porous materials. It's a really clever use of separation under conditions and also arguably separation in space. One last illustration, a medical example of an automatic implantable cardiac defibrillator, or AICD. This is a device that defibrillates the heart. It shocks the heart, but not all the time like a pacemaker, but only when it's needed. So while the heart is beating normally, the defibrillator just sits there inactive. If the heartbeat becomes erratic, the defibrillator fires. And it overcomes an obvious contradiction. You don't want it firing all the time because it's going to consume battery power and it's also going to probably cause more harm than good. But you definitely want it to fire when you need it, because if it doesn't, you'll die. So separation upon conditions. And also the use of inventive operator feedback. If you haven't noticed already, you can convert technical contradictions to physical contradictions and vice versa. Why would you want to do this? Well, because the technical contradictions involve 40 inventive principles, and I confess there's actually more than 40, so it can become unwieldy. On the other hand, the physical contradictions are addressed using those 4 handy-dandy separation principles. Now you pay a price because the separation principle itself doesn't tell you exactly what to do. It doesn't tell you to change the phase or introduce a field or use a porous medium. But it's a quick and easy approach when you need a quick solution and you want to get over a stumbling block or you've hit a brick wall in trying to solve a problem that involves a contradiction. Not only are the inventive principles and separation principles interchangeable, they're also related, as you may have noticed. For example, segmentation is obviously an example of separation in space, and prior action is an example of separation in time, and so forth. I made this little table. It's not an official TRIZ table, but it helps me also just interrelate the 40 operators and the separation principles. Here's a few more rapid-fire examples, because the more examples you see, the more clear these principles become. The Band-Aid, you remember, has the contradiction that it needs to be sticky, and it also needs to be not sticky. And this is where we applied segmentation or local quality. But it's clearly an application of separation in space. The light bulb, what was that contradiction? Well, there's a filament that needs to be hot in order to produce light, but if it's too hot, it's going to burn, it's going to oxidize and consume itself. So this was solved using local quality inert environment, or put another way, by putting a shell, a glass bulb, around the filament, having a vacuum on the inside and allowing atmosphere to be on the outside, and thereby protecting the filament from oxygen. Separation in space. My favorite, inductive stovetop. Remember, this uses universality and also replacement of a mechanical system. The contradiction is it must transmit energy to the pot in order to boil the water, but not transmit energy to everything else, the hand, the tabletop. This is another separation in space. Detachable shower head. It must be attachable or fixed in space so that you can use both of your hands, but it needs to be movable under other circumstances so you can move it around and carry it in your hand. So there's an example, separation in time. Transition lenses. You want them to be dark and you want them to be transparent, but not at all times. You want them to be dark when you're outside in the sun, and you want them to be transparent on the inside. Another example of separation under conditions. And one last example. We saw epoxy. It's an example of transformation of physical and chemical states of an object, and it's also the contradiction. You want it to be liquid at one time, you want it to be solid at another time, separation between parts and the whole. You might be asking that if we can replace the 40 inventive principles with the 4 separation principles, why don't we just do that all the time and discard the 40 inventive principles? Well, it's because the separation principles aren't that useful all the time. Take these 4 examples. The vane illuminator. What exact separation in space or time or conditions is presented by this problem? It's not immediately apparent. Electric cautery, it's an obvious case of rushing through or transformation of physical state or converting harm to a benefit, but it's not clearly a physical contradiction or an application of separation of anything. The juice box straw is an example of nesting. It arguably is an example of separation in space or in time. You want it to be short at one time and long at another time, or short when it's being stored and long when it's being used. But thinking in terms of nesting and dynamicity is a more fruitful application of the TRIZ principles. The iPhone, it's clearly an invention, but it's not really solving any separation related problem. It's more just a mashup of multiple functions, and hence illustration of universality. So a word of warning is not to go overboard with the use of separation principles. Separation isn't always a good thing. All right, that concludes the lecture at 27 minutes 38 seconds. And now it's your turn. You go ahead and try your hand at separation principles, see the assignments on Blackboard, and I look forward to working with you again on Thursday.